Okay, so the next thing we want to talk about in topic 2 is two-dimensional vectors. Up until this point, we've only worked with speed on a straight line, and we've had two different possibilities for direction. We've either gone in a positive direction going up or right, or in a negative direction going down or left. So what we could do is we could think about movement in the entire plane, and we could allow ourselves to move off from our straight horizontal line or vertical line at different angles. And so if we do that, there are infinite possibilities for the directions that we can move in. If we think about all 360 degrees that we could turn in. And so what we can do is we can represent the magnitude, how fast we're going, and the direction, the angle of our movement with two-dimensional vectors. And so I think a lot of you have probably already covered these in physics. So hopefully this will be really easy for you and just a review of some things. So two-dimensional vectors. A two-dimensional vector, it's an ordered pair of real numbers, and how we give its component form. So we have our two coordinates with a comma in the middle, and then you have these little brackets. They almost look like angled arrowheads on either end. So A comma B. So the numbers A and B are the components of the vector V. And so if we want to represent, so the standard representation is the arrow from the origin to the point AB. So what you have down here in this graph, so this is vector AB, and so we start at the origin and we're ending at that point A comma B. Okay, so the magnitude of V is that, you can kind of think about that as the speed of the object, and so we think about that to be the absolute value of it, or the length of the arrow. Okay, so the length of your arrow is going to be related to how fast your object is moving. And then the direction is just the direction in which the arrow is pointing. So vector 0, which is just the point at 0, 0, is called the zero vector, and it has zero length and no direction. Alright. So the magnitude of a vector, just a quick review, the magnitude of a vector is the absolute value of the vector, A comma B. It's the non-negative real number, and how you can figure it out is this square root of A squared plus B squared, and hopefully this reminds you of the distance formula, right? So if your origin is starting, or if your vector is starting at the origin, then it's really easy to find your magnitude of that. Equivalent vectors are just vectors that you can slide all over the plane. So we've got this one that starts at the origin and goes off to 3, 4. If I pick it up and just slide it up right here, it has the same magnitude or length. It's just starting at a different point. It has the same angle, we can tell that because it's parallel, and it goes the same distance, but it just ends at a different point. Okay, so situations like that where you have vectors of equal magnitude and equal direction but in different parts of the plane, we just call those equivalent. So the direction angle of a vector, or specifically of a non-zero vector, it's the smallest non-negative angle theta that you would form with the positive x-axis as your initial ray, and the standard representation of it is the terminal ray. So if we just think about this for a second, the smallest non-negative angle theta. So if we're working with the smallest non-negative angle theta, and so if you have some vector shooting off that way, well, then that means the angle that we're going to use to measure it is going to start from our positive x-axis and go up to it. Okay, and then likewise, if we have the same thing but over here, you know that we could start over here and measure it. We could start from the negative x-axis, but that doesn't qualify what we want. So we'll still start from the positive x-axis, and then in this case you have an obtuse angle. So denoting vectors, so some textbooks do this a little differently, but your textbook uses boldface variables to represent the vectors. So boldface U and boldface V are vectors U and V. Now, when you're using your own handwriting, it's sometimes tough to write letters like that in bold. So what we can do with our own handwriting is just throw an arrow on top. And then we can also use those angled brackets that look almost like arrowheads on either end to distinguish them from a point, right? So you can have the vector xy, and so you've got these angled brackets on either end, and then the point xy that has parentheses on either side of it. And then it has this disclaimer. It's not uncommon to see x comma y in parentheses used for both, especially in handwritten form. So some people will write out their vector using the parentheses instead of the angled brackets. I try to avoid that just for confusion's sake, but some people get away with it. I think on the AP exam, they're pretty clear about what's a vector and what's not. I don't think they do that on the AP exam. Alright. So head minus tail rule. So if you have some arrow that has an initial point x comma y and then a terminal point x sub 2 comma y sub 2, that's going to give you the vector x2 minus x1 comma y2 minus y1. So all we're doing is we're taking the coordinates of our terminal point, subtracting our initial point. Okay, so head minus tail. So terminal minus initial. Alright, so for example 3, you have to find the magnitude and the direction angle of the vector 1 root 3. Okay, so our magnitude is just going to be, we're going to use that formula a squared plus b squared, which in this case is going to be the square root of 1 plus root 3 squared. 1 squared plus root 3 squared, which is going to give us the square root of 1 plus 3, which is 2. Okay, so the magnitude of our vector is 2. Now, to find the direction, okay, well, if you can find your direction with sine or cosine. So if you remember back from what you learned in trig, okay, cosine theta is x over r. And this magnitude that you found, you can think about that as also your r value. Okay? So, and then your x is just the x that's given, which is 1. So, in this case, we have an x of 1, our magnitude is 2, okay? So then what you have is cosine of theta is 1/2. Well, you know, where does cosine equal 1/2? If you think back to your special trig values, this is going to be theta is going to be pi over 3, which is 60 degrees. Okay? And so that'll be the direction of your vector. In this case, I guess you could also use the sine if you wanted. Some students are pretty quick with that. I would have liked to have used, I would have just liked to have used the cosine because, well, my cosine is 1, and maybe I just remember that really quickly. Or my x value is 1. But for sine, you would just plug in your y value, right? So if you wanted to use sine, I guess it would be just as easy. Maybe it just all depends on what you remember faster. So your sine is y over r, and then your y would be root 3 over 2. Yeah, so then I guess you would get theta is going to be 60 degrees. So it's just whatever you remember faster, cosine or sine. Alright, example 4. So for example 4, we want to find the component form of a vector with magnitude 3 and direction angle 40 degrees. Okay. So first off, I'm going to kind of want to visualize what's going on here. right? So if we have a magnitude of 3, and then this angle is 40 degrees, okay? And then, so if we know, well, okay, if I take the cosine of 40 degrees, that's going to be some x over r, and I know I don't quite know what my x is, but I know that my r is 3. So then I could multiply both sides by 3, and I would get 3 cosine 40 is x, and then I could punch that into my calculator, and I would get x is approximately 2.298. Okay, so I have an x component. And then to find sine, well, sine of 40 degrees is going to be y over r, which is going to be y over 3. So then we could say that 3 sine 40 is y, and so y is approximately 1.928. And so then our vector with the coordinates that we've been given, or that we just found, the components, I'm sorry, not the coordinates, is going to be 2.298 comma 1.928, right? So your x component and your y component, and that's it. Alright, so for example 5, we want to find the component form of a vector with magnitude 5 and direction angle 100 degrees, okay? So again, we can roll through this, and x is going to be 5 cosine 100, and so then we punch that into our calculator, and we're going to get about negative 0.868, and then y is going to be 5 sine 100, and that's going to be about 4.924, okay? So then we would say that our vector is approximately negative 0.868 comma 4.924. Okay, now if we think about it, this makes sense that this is negative, because if you picture where 100 degrees is, here's 0 degrees, here's 90 degrees, so 100 degrees is going to be somewhere in the second quadrant. And so, you know, in the second quadrant, your x's are negative, but your y's are positive. So it makes sense here that your first component is negative and your second component is positive. Alright, and then because vectors have magnitude, we have to be able to do things to them, like add and subtract them and multiply them. So we've got to talk about vector addition and scalar multiplication. So let's say u represents our vector, one of our vectors, and v represents another vector, and let's say k is some real number or some scalar. We can multiply the vectors by k, right? And then in that case you just multiply both components by k, and so we would say the product of the scalar k and the vector u is just ku sub 1 comma ku sub 2. You can also add your vectors, and that's really easy to do. If you wanted to do u plus v, you just add your separate components, right? So you add u sub 1 plus v sub 1, and then u sub 2 plus v sub 2. And if you wanted to flip your vector around and find the opposite of it, you would just multiply the whole thing by negative 1. And when you flip it around, what you're doing is, you can think about that in a bunch of ways. It's almost like you're rotating it 180 degrees, or you could think about, yeah, I think that's probably the safest bet to say for now, is that when you flip it, it's almost like rotating it 180 degrees, okay? So that's one way that you can picture it being laid out in the plane. And then the unit vector is a very special vector. The unit vector is just the vector v over the absolute value of v, and that's a vector of magnitude 1. And so its component form is just cosine theta, sine theta, and then theta is going to be your direction of angle. So we can have our unit vector going off in any at any angle, but it's always going to have a magnitude of 1, okay? And so sometimes we call v over absolute value of v the direction vector of v. So tail to head and parallelograms. So an easy way to add two vectors together, or kind of picture what their sum would be, is to just add them tail to head, right? So if I want to do vector u plus vector v, I would just, let's say vector v originated down here in the origin, and let's just pretend that, well, we have it on this graph right here. Okay, so u is going up here, v is going over here, and let's say we want to add together u plus v. So then what you could kind of picture happening is you take your vector v, and then you just slide it up, and you take the tail of v, and you put it at the head of u, and then you can connect the dots. That's what we did in this graph here. And then whatever angle this is, and then whatever magnitude this is your new vector. And so so we've got a few things written up here about this. So the sum of two vectors can be represented geometrically by arrows in two ways, right? So you can represent them in arrows with this triangle, and then the base formed connecting the two legs of the triangle. Or you can have the parallelogram representation, and you've got your standard vector of u and your standard vector of v, and then you kind of draw the parallels on each one and then connect the dots, and that makes your parallelogram. Now, scalar multiples. So this is somewhat related to what I was saying about flipping a vector. So we can have scalar multiples of vectors, and we can stretch and shrink them. So let's say we have vector u, and we can stretch it if we multiply it by a scalar that has an absolute value, let's see, well, what does this say? That has an absolute value greater than 1, and then we would shrink it if we're multiplying it by an absolute value less than 1. So this 1/2 u, right, the whole vector is being cut in half. The other thing that we can do is we can flip them. So in this case, this last vector here on the right, I'm taking my vector of u and I'm multiplying it by a -2. So in that case, I'm multiplying it by something, by a k scalar that's less than 0, and so what that does is it just flips it, and you point it in the opposite direction. So that kind of goes along with what I was saying about rotating 180 degrees, right? So if you pictured this in a coordinate plane, what you're doing is you're taking this vector and you're rotating it 180 degrees, and that's why it's flipped that way. So now we have some examples where we can do the operations on these vectors. Alright, so this takes us to example 6. So we have vector u is -1, 2, v is 4, 8, and then we've got to find these. So for part A, what we're going to be doing, you can start off by thinking we're going to have 2 multiplied by the vector -1, 2, and then we're going to take our vector v, multiply that by 3, so we'll have 3 times the vector 4, 8. Okay, and so if we carry that out, we'll get negative, oops, put in my brackets here, -2, 4 plus 12, 24, and then what we can do is we can add these values together, and so a -2 plus 12 is going to be a +10, and then a 4 plus a 24 is going to be a 28. Right, and so that's our answer there. So then for vector u minus vector v, so we just subtract our components, and so that's going to be -1, 2 minus the vector 4, 8, and this is going to give us let's see, negative 1 minus 4, that'll be a negative 5, and then 2 minus 8 will be negative 6. So you get negative 5, negative 6. And then 1/2 v for part C, well, all we're doing here is just multiplying vector v by 1/2. And then, but we're also taking the absolute value of it, so we're also finding the magnitude, okay? So, well, 1/2 of v, if we take our components of vector v, 4, 8, and we cut those in half, that's going to give us 2, 4. But then if we take the magnitude of that, the magnitude of 2, 4 is just going to be the square root of 2 squared plus 4 squared, which is the square root of 4 plus 16, right? Which is going to be the square root of 20. And you can leave it like that, or you can simplify that to a decimal, or to 2 root 5. And that's it for example 6. So some basic operations to perform on these vectors. And I'd say they're pretty much common sense and they're pretty intuitive. If you have to add them, you add your components. If you subtract them, you subtract your components. And then you can multiply by scalars. The one thing that might not be so intuitive is when you have to find the absolute value or the magnitude. And that's just your distance formula. You square your components, add them together, and then take the square root. Okay? And then the last slide in topic 2 is just this slide summarizing our properties of vector operations, right? So this is the commutative property right here. So if we do u plus v, that's going to give us the same answer as doing v plus u. This is the associative property. If we have 3 vectors, u, v, and w, and we want to add them all together, we can do u plus v first, or we could do v plus w first, and we get the same answer. If you add 0 to anything, you're just going to get what you started with. If you add the negative version or the opposite and you flip it and then you add those together, well, they'll cancel out and then you'll get 0. If you want to take any vector and multiply it by 0, you'll get 0. If you take any vector and multiply it by 1, you'll just get that original vector. If you, okay, so this is saying multiplying it by 2 coefficients. Well, you can multiply the vector by 1 coefficient first and then the next, or you can multiply your coefficients and then multiply by the vector. And then this is just the distributive property, right? So if you have u plus v and you want to multiply that by a, you could do a times u plus a times v, do the multiplication first and then add together. And then this is just the sum. You can add a plus b and then multiply it by u, or you could take the vector and distribute that across your a and your b, right? And so those are all properties that you are familiar with just from being in Algebra 1, okay? And that's the end of Chapter 10, Topic 2.